Dear students, in this class we are going to discuss about per unit representation. What is meant by per unit system? The per unit values for transformer impedance, voltage and current are identical when referred to the primary and secondary. That is, no need to reflect impedances from one side of the transformer to the other side. The transformer is a single impedance. The second point for the per unit system is the per unit values for various components lie within a narrow range regardless of the equipment rating. And third point is the per unit values clearly represents the relative values of the circuit quantities, and many of the ubiquitous scaling constants are eliminated, and it is used ideal for the computer simulations. So we are going for the per unit system. How to calculate the per unit value? The key problem in analyzing power system is a large number of transformers. So it would be very difficult to continually have to refer impedances to the different sides of the transformers. This problem is avoided by normalization of all variables. This normalization is known as per unit analysis. The formula for per unit is equal to actual quantity divided by the base value of the quantity. The quantity in per unit is equal to actual quantity divided by the base value of the quantity. Let us see the per unit conversion procedure for single phase. First step, you have to pick a single phase VA, that is rating base for the entire system, that is SB. And second step is pick a voltage base for each different voltage level, that is VB. Voltage bases are related by transformer turns ratios. Voltages are line to neutral value. And third point is calculate the impedance base ZB by using the formula VB square divided by SB. Then calculate the current base IB, that is equal to VB divided by ZB. And finally convert actual values to the per unit value. We have to note one point, the per unit conversion affects magnitude only, not the angles. Also, per unit quantities no longer have units. That is, a voltage is 1.0 per unit only, not 1 point per unit volt. Let us see the per unit value for some quantities. First, if you take the value of A, per unit equal to A actual by A base, I per unit equal to I actual by I base, V per unit equal to V actual by V base, S per unit equal to S actual by S base, Z per unit equal to Z actual by Z base, R per unit equal to R actual by Z base, X per unit equal to X actual by Z base. These are the formulas used to find out the value of A per unit, I per unit, V per unit, S per unit, Z per unit, R per unit, X per unit. If any two of the I, V, Z, S is known, remaining two can be fixed automatically. The formula for Z equal to V by I, Z base equal to V base divided by I base, ZB equal to VB square divided by SB, Z per unit equal to V per unit by I per unit, S per unit equal to V per unit into I per unit. Let us see the example. A 5 kVA 400 bar 200 volt 50 Hz single phase transformer has the primary and secondary leakage reactance each of 2.5 ohm. Find out the total reactance in per unit. That is the question. The given values are SB is equal to 5000 VA and the primary base voltage is equal to 400 volt, that is VB1. Secondary base voltage VB2 equal to 200 volt. Then we have to find out the value of X1E, that is equal to X1 plus A squared X2. It is the formula. Therefore find out the value of A, that is the turns ratio N1 by N2. 400 divided by 200 is equal to 2, that is equal to A. Therefore X1E is equal to 12.5 ohm. Then X per unit equal to X actual by Z base. ZB1 equal to VB1 squared by SB. VB1 is 400, therefore 400 square divided by 5000 gives 32 ohm. X per unit is equal to X actual by Z base. So 12.5 divided by 32 is equal to 0.39 per unit. Then X1 per unit equal to X1 divided by ZB1. X2 per unit is equal to X2 divided by ZB2. Advantages of per unit representation. Ordinary parameters vary considerably with variation of physical size, terminal voltage and power rating, etc. While per unit parameters are independent of these quantities over a wide range of the same of apparatus. In other words, the per unit impedance values for the apparatus of like ratings lie within a narrow range. It provides more meaningful information. The chance of confusion between line and phase values in a three-phase balance system is reduced. A per unit phase quantity has a same numerical value as the corresponding per unit line quantity regardless of the three-phase connection whether star or delta. Impedances of machines are specified by the manufacturer in terms of per unit values. The per unit impedance referred to either side of a single phase transformer is the same. The per unit impedance referred to either side of a three-phase transformer is the same regardless of the connection whether they are star star, delta delta or delta star. The computation effort in power system is very much reduced with this use of per unit quantities. Usually the per unit quantities being of the order of unity or less can easily be handled with a digital computer. Manual calculation are also simplified. Per unit quantities simply theoretical deduction and give more generalist forms. Then we will see the losses of transformer. The losses that occur in transformers have to be accounted for in any accurate model of transformer behavior. We know the transformer has copper loss and core loss. Copper loss is I squared R loss. Copper losses are the resistive heating losses in the primary and secondary winding of the transformer. They are proportional to the square of current in the winding. Then eddy current loss. Eddy current losses are resistive heating losses in the core of the transformer. They are proportional to the square of the voltage applied to the transformer. And hysteresis loss. They are associated with the arrangement of the magnetic domain in the core during each half cycle. They are the complex nonlinear function of the voltage applied to the transformer. And finally leakage flux. The fluxes which escape the core and pass through only one of the transformer leakage fluxes. These escaped fluxes produces a self-inductance in the primary and secondary coils, and the effects of the inductance must be accounted for. Nameplate rating of transformer. It is used to specify the voltages and current. In transformer, both voltages in the primary and secondary side should be in the range of maximum safe voltages. If current varies, the temperature in the coil of the conductor changes, which may lead to damage. Hence, the current should be in the maximum range. Transformer applications. Voltage level adjustment, that is step up and step down transformer, is used for the voltage adjustment. Then it is used for the voltage and current measurement, that is potential transformer and current transformer is used for the voltage and current measurement. Then it is used for the isolation purpose for the safety. Then the impedance matching for maximum power transfer from the source to the load. These are the applications of the transformer.